Have you ever stopped to think about how a platform like Twitter or Discord actually works? I mean, how they generate literally billions of unique ideas for every single post, every message, every interaction without ever messing up and creating a duplicate. It's a massive engineering problem, and today we're going to pull back the curtain on how they do it. I mean, just try to wrap your head around the scale. We're talking hundreds of millions of new things happening every single day, and each one needs its own unique, sortable number generated in a blink of an eye across thousands of servers all over the world. How on earth do you pull that off without the whole thing just falling apart? All right, so here's our game plan. First, we're going to really define the problem itself. Then we'll walk down 3 different roads that seem like good ideas, but are actually dead ends. After that, we'll get to the main event, Twitter's brilliant Snowflake solution. We'll dissect it piece by piece, and finally, we'll look at how it handles some really tricky real-world curveballs. Okay, so before we can even start looking for an answer, we have to lay down the rules of the game. This isn't just about making any old unique number. It's about making a very specific kind of number that can survive in the wild, chaotic world of a massive distributed system. Here are the non-negotiables, the absolute must-haves. First, obviously, the ID has to be totally unique, no exceptions. It also has to be a 64-bit number, because numbers are way faster for databases to handle than, say, text. Now, this next one is absolutely critical. It has to be sortable by time. An ID created a second ago must be numerically bigger than one created a minute ago. That's how you get a chronological Twitter feed. And of course, the whole system has to be rock solid and screaming fast. We're talking over 10,000 of these things per second. Now, your brain is probably already spinning with a few obvious solutions. But, as we're about to see, the things that work for a small website completely fall apart at this kind of scale. Let's explore why these common ideas just don't make the cut. So, our first attempt might be something called multi-master replication. It sounds complicated, but the idea is simple. You have one server create all the odd-numbered IDs, 1, 3, 5, and so on, and another server create all the even-numbered IDs, 2, 4, 6. Pretty clever, right? They never step on each other's toes. Well, the problem is, what happens when you need to add a third server? Or a fourth? The whole setup gets messy really fast. But the real deal breaker is this. ID number 6 could actually be created after ID number 7 if the servers are busy at different times. So that crucial time-sortable requirement? Broken. It's a no-go. Okay, so what about the good old UUID? A universally unique identifier. Any computer can just spit one of these out on its own, and the chance of a collision is so small it's basically zero. It's totally decentralized, super simple. What's not to love? Well, it turns out there's a lot not to love, actually. It fails on 3 key points. 1, it's 128 bits, which is double our 64-bit budget, making it way less efficient to store. 2, it's not a number, it's a string of text, and databases are way slower at sorting text. And 3, the big one, they're completely random. They have no concept of time, which makes them totally useless for creating anything like a timeline. All right, that brings us to attempt number 3, the ticket server. The idea here is simple and intuitive. You just have one super powerful server whose only job is to hand out the next number in line, kind of like the ticket dispenser at a deli. You need an ID, you just ask it for the next one. And this is a great solution, right up until that one server crashes. If your ticket machine goes down, the entire platform grinds to a halt. No new tweets, no new messages, zilch. You've created a giant bottleneck and a single point of failure, and that's pretty much rule number 1 of what not to do in distributed systems. So, if our standard database tricks fail, UUIDs fail, and centralized servers fail, what's left? This is where the engineers at Twitter had a truly elegant breakthrough, a solution they called Snowflake that brilliantly sidesteps all of these problems. The big aha moment was realizing they didn't need a central server to coordinate everything. The solution wasn't another piece of hardware. It was a structure. It was just clever math. They designed a way to pack all the information they needed, uniqueness, time, and which server made it, all inside a single, compact 64-bit number. So let's pop the hood on this thing. Let's do a little surgery on this 64-bit number and see what's actually inside. This is where the pure genius of the whole system really starts to shine through. Okay, check this out. The very first bit is just a sign bit. We ignore it. But the next 41 bits are the heart of the whole thing, a timestamp measured in milliseconds. This is what makes the IDs perfectly sortable by time. Then, the next 10 bits are split into a data center ID and a machine ID, which together give a unique fingerprint to the server generating the ID. And finally, the last 12 bits are a simple counter that ticks up if you need to make more than one ID in the exact same millisecond. Now that 41-bit timestamp, it has this amazing side effect. It gives you enough milliseconds to run this system for, get this, 69 years from whatever start date you pick. 69 years. That's some serious long-term thinking baked right into the ID itself. It's an incredible example of future-proofing your design. And remember that 12-bit sequence number at the end? That's the secret to its insane speed. It means a single machine can generate up to 4,096 unique IDs in the same millisecond. That's how you handle a massive sudden spike in traffic, like when a tweet goes viral. And finally, you combine those data center and machine ID bits. That gives you a unique 10-bit signature for each server. This is what makes the system truly distributed and scalable. It means you can have up to 1,024 different machines all generating IDs at the same time, with zero coordination because each one stamps its own unique fingerprint right onto the number it creates. So the design is brilliant, absolutely. But how does it actually work in the messy real world? And, what happens when things inevitably go wrong, like a server's clock deciding to go on a little time-traveling adventure? Well, when it comes to actually using this, you've got two paths. You could build a central service to hand out IDs, but we've already seen why that's a bad idea. It just recreates the bottleneck. The far, far better way is to just embed the ID-generating logic right into the application itself, as a library. That means the ID is created instantly, right there on the local CPU, with zero network delay. That's the key to making it so incredibly fast. Okay, now for the final boss question. This is the classic system design interview problem. A server's clock, because of network time sync, can sometimes jump backwards by a few milliseconds. If that happens, you're in danger of creating duplicate IDs. So, how does Snowflake handle this nightmare scenario? The solution is actually really simple and elegant. The generator just remembers the timestamp of the last ID it made. Before it makes a new one, it checks the current time. If the current time is less than the last time, it knows the clock has gone backwards. So it simply refuses to make an ID or just waits a few milliseconds for the clock to catch up to where it was. It's a simple little safety check that prevents a massive data disaster. So let's put it all together. You can see right here why Snowflake is the clear winner. It's unique, it's highly scalable, and it's perfectly time-ordered. It ticks all of our boxes. Its only real con is that you need to keep your clocks reasonably in sync. But as we just saw, there's a safety net built right in for that exact problem. And that really brings us to the big takeaway. Sometimes the best solution to a massive engineering problem isn't just throwing more servers at it. Sometimes it's about being smarter with the data you already have. It's about clever math. And it really makes you wonder, what other huge internet problems are being solved right now, not with brute force, but with a simple, elegant little equation?